Here we go. Number 43. When you're new at this, you just shake your head and you just go, what are you doing to me? What's this big gobbledygook? But once you've done integrals, then you look at this and you say, geez, they're just really rigging this whole thing. And so here's what's going on, is that you're supposed to remember and also recognize at a glance that the derivative of sine inverse of x is 1 over square root of 1 minus x squared. And so you're supposed to see that 1 minus x squared and have a Pavlovian experience where you just react uncontrollably and you say, oh my God, that must be the derivative of sine inverse of x. If you're not at that level, then you don't understand that anybody could ever be at that level. But when you've done this a lot and you've committed this thing right here to memory, then it is possible to have that experience. So that's the design. Okay, so when I look at this, I'm not saying that you're supposed to do this immediately when you're first learning integrals, but when you've done a lot, I see this sine inverse x, and I also see this, and I immediately say I want my u to be sine inverse x. I want du, well I don't want, but du will then become 1 over square root of 1 minus x squared dx. I go to substitute for everything I see here. The sine inverse is in the denominator, so that's 1 over u. And then the dx over square root of 1 minus x squared is exactly du. So you see how rigged that is? It converts perfectly into 1 over u du, which is at ln absolute value u. And then I can put in u equals inverse sine to complete the problem. Okay. Number 44. Okay, now we're getting into real disguise type things. You might start to think, geez, it's unfair. It's unfair. Maybe. Excuse me. Okay, so here's what you try, right? You immediately say, okay, well, I gotta find something to pick for u. Maybe I pick u equal to 1 plus x to the fourth because I like having 1 over u. And then du is going to be 4x cubed dx. And you go to substitute, and what you really need is you need there to be an x cubed up here. So if it was rigged to be 1 over u du, we would have had x cubed on the top, but we don't. So it's not rigged for that. Rigged for something else, but this one's a little bit more disguised. So then you say, okay, well, if I have an x up here, what would you like to have? Wouldn't you like to have u equal to x squared? Because then du would be 2x, and then you would have that x dx to substitute. So that's the design here, is that, and you might have to play with this and come back to it before you think about this or try it. But what's going on here is, this didn't work. We're going to do, let me rewrite it for you. This is the same as x over 1 plus x squared squared. And looking ahead, if you were to pick x squared to be u, and I was successful at making the substitution, then I would have 1 over 1 plus u squared, and that's one of the ones we know. It's a prerequisite. Okay, so that's the one we know, 1 over 1 plus u squared. This is 1 over 1 plus x squared squared. So I'm going to make u equal to x squared, then du is 2x dx. This integral now becomes, on the bottom I have 1 plus u squared. On the top, well, I have x dx still to account for, and x dx, you can see here, x dx is equal to 1/2 du. Okay, so I have exactly this integral right here. This is now equal to 1/2 inverse tangent of u, and then I can put u equal to x squared in to complete the problem. Okay, this is a red numbered problem. Now we have the previous one fresh in our mind, so you see that 1 plus x squared in the denominator. That reeks of inverse tangent. The design of this problem is to really think of it as two integrals. This is the integral of 1 over 1 plus x squared dx plus the integral of x over 1 plus x squared dx. This one here is an inverse tangent. We can do it immediately. And then over here, this is a classic 1 over u du. I'm going to let u equal 1 plus x squared so that the denominator is u, and then du is 2x dx. When I convert this integral, I get, on the bottom, I get u. Then I have x dx to account for, and that is equal to 1 over 2 du when I bring this 2 over to the other side. Okay, so I have 1/2 ln absolute value of u, and then that's 1/2 ln u is, in this case, 1 plus x squared. And this is one of those cases where 1 plus x squared is always positive, so you do not need the absolute value, and so I would expect the book not to have that in the solution, or if you find it online. It won't have the absolute values, not because the absolute value is wrong, but because it's not doing anything. 1 plus x squared is always positive. This is a good one to put on your list of things to do before an exam, because it's got two things to remind you of, the inverse tangent and also this 1 over u du, and also the trick of splitting the integral into two fractions, this fraction and that fraction, and then making them manageable integrals, whereas the way it is there, it's harder to do in its current form. And I said to leave off the absolute value, so I'll also do that. This is 1/2 ln 1 plus x squared, since 1 plus x squared is greater than 0. Number 46. Number 46. We have the integral of x squared square root 2 plus x. Now this is a tricky one, okay? This is the kind of thing you'll have maybe on an exam, because they gotta separate people. It's called the curve setter right here. Okay, and it's one of those ones where it's hard to figure it out on your own. And once you see the trick, then you can add that trick to your repertoire, and you'll start to get this one too. But it's hard to figure it out on your own. You get stuck right away. Okay, now whenever I see a square root, I've been coaching you, pick the thing inside the square root is the u. And this is no different, except we're going to get stuck here. So u equals 2 plus x, and then we always take the derivative, so du equals dx. And then when I go to convert here, I do have square root of u by design. The dx is du, but I still haven't accounted for the x squared. And we can get around that. So when you do a lot of these integrals, you're so used to, once you pick the correct u, it popping out and you being able to do the integral. This one doesn't have that, so then maybe you'd move on and try to find something else to pick for u. But in fact, we can do this. What we need to do, though, is we want x squared, and we can solve for x here. X is equal to u minus 2, so that means that x squared is equal to u minus 2 squared. And then you say, well, how does that help me? Because now I have square root of u times u minus 2 squared du. And while these two integrals are equivalent, if I can do this one, then I've essentially done this one. But here's the difference. When you have the square root of u as opposed to the square root of 2 plus x, you can now combine this term with the terms from here once you multiply it out, because it's all just one u inside the exponent as opposed to a quantity 2 plus x. Let me show you what I mean. So I'm going to rewrite this integral as root u times u squared minus 4u plus 4 by multiplying that out, the u minus 2 squared. And then I can incorporate the root u in and just have them all as exponents. So this u squared is the same as u to the 4 over 2, and the root u is u to the 1/2. So the first term here is going to become, it's u to the 4 over 2 plus 1 over 2, which is u to the 5 over 2, minus 4. This u here is like having u to the 2 over 2. It's u to the first power, which is 2 over 2. I add a half to that, I get u to the 3 over 2, plus 4 u to the 1/2, all times du. And now I can integrate. Okay, I'm going to add 1 to 5/2, which is like adding 2 over 2. So I get u to the 7/2 divided by that very 7/2, which is the same as multiplying by 2 over 7. Here I have 4. I'm not going to try to be a hero and do it all at once. I'm going to get u to the 3/2 plus 1, which is the same as adding 2 over 2. So I get u to the 5/2 divided by that very 5/2, which is the same as multiplying by 2 over 5. And then I have my old friend u to the 1/2, and that's 2/3 u to the 3/2, and then plus c. Now we can do a little housekeeping, and remember that u is equal to 2 plus x. This becomes 2/7 times 2 plus x to the 7/2, okay, minus 8 over 5, 2 plus x to the 5/2, plus 8 over 3, 2 plus x to the 3/2 plus a constant. And it would be, for those of you who like a little puzzle, a little challenge, take the derivative of that and see if you get back to this. You'll have to do a little algebra to do it because it's got to reduce a bunch. But it will be true. Okay. So let's recap what happened here. Okay, we picked our u to be 2 plus x, and we got stuck when we went to do the substitution here, because we had this extra x squared, which I should write there. And it felt like we were stuck, but the way we squirmed out of our predicament was that we solved for x here, and we got u minus 2, and so x squared is u minus 2 squared. Now I was able to incorporate this u to the 1/2 into all these other exponents and actually get the integral done. Okay, it's a good one to repeat for yourself. Don't just look at, go, yeah, oh, yeah, I get it. Oh, no, I can do that. Yeah, oh, I got it. And then go do it yourself. It's a good one. When you get stuck, or if you get stuck, just look back at where you got stuck, see what the extra step is, and then try to get from the beginning to the end yourself. Okay, here's another opportunity, I think, to do that. We have number 47 is x times 2x plus 5 to the 8th. So the idea of the 8th power is it just eliminates the possibility of multiplying it out. That's what they're saying. Don't even multiply that out. Don't even think about it. Because who wants to? So no one wants to. So it's just, if it was 4th, maybe you'd be tempted. But 8th, no way. Okay, so we've been trained to pick the stuff inside the parentheses to be u. And so we'll try that. We get 2x plus 5. And then du is equal to, well, it's just 2 dx. And so look what happens. When I go to do the substitution, I get u to the 8th by design. The dx is 1/2 du by solving for dx here. But I still have that x out front. So that's not good. I mean, I'm not going to be able to do this integral. It's got to all be in terms of u. I've got to account for everything I see in the original integral. But again, we can squirm out of this by solving for x here. We have u equals 2x plus 5, so u minus 5 is equal to 2x, and so we get x is equal to 1/2 u minus 5. Okay, and I can take that version of x and put it right there. Okay, so I have 1/2 integral, and I'm going to put all that in. I have 1/2 u minus 5 times u to the 8th. Let's do a little pre-housekeeping before we do our integral. We'll put the 1/4 out there, and then I have u minus 5 u to the 8th. But see, this one's manageable. I don't mind multiplying this out. It's 1/4 u to the 9th minus 5 u to the 8th. I can do that. This is u to the 9th, and this is not an a, it's a u. Well, I'm ready to go now. Okay, I have 1/4, and then on the inside, I'm going to have u to the 10th over 10 minus 5 u to the 9th over 9. And then we'll clean all that up. We get u to the 10th over 40 minus 5 u to the 9th over 36, all plus c. And then we can put back what u was in terms of x. U is equal to 2x plus 5. Let's go put that in now. Our final answer is 2x plus 5 to the 10th over 40 minus 5 times 2x plus 5 to the 9th power over 36. There we go. Okay, again, go back and do this one yourself. It's got this little extra step in it. You pick u, you kind of get stuck, and you go back and you say, oh, I can get what I need to do the substitution. There's that extra x, but I can go back to the u here and find out what x is in terms of u and put it in there. We never had to do that before these last two examples, so that's a new trick. And like I said, that's a curve setter. That's the kind of thing they put on an exam to I gotta get them. I gotta get these guys. Okay, number 48, same kind of deal. You get conditioned to pick the thing inside the parentheses, and it's a good thing to have, but sometimes you get stuck, but we'll get out of it. Now, here's another one to think of, is that what would you like to have? If you picked u equal to x squared plus 1, as you might be in the habit of doing by now, then you'll do dx, and that's 2x dx. And you need that x dx, right? So we might want to borrow an x from here. So we can think of this as x squared squared plus 1 dx. I need one of those x's for my substitution. When I do this one, the square root is going to be accounted for as u. The x dx, well, that'll be 1/2 du. We've done that a few times, so I'll put the 1/2 here, and the du, that accounts for x dx right here, but I still have that extra x squared here that I haven't accounted for. But the way we can get it is like we've just seen in the last two examples. We could solve for x squared here and get u minus 1. I can put that u minus 1, bring it right there. 1/2 times u minus 1 root u du, and now we should be home free. It's the integral. I'm going to multiply that out so I get just single exponents. U to the, this is the 1/2 power, this is 1 power, so I get 3/2 total, minus u to the 1/2. Now I can do my integration. Here I get 2/3, oh, I get 2/5, excuse me. U to the 5/2 minus 2/3 U to the 3/2 plus C. Then some housekeeping. I'll get 1/5. Remember, U is equal to x squared plus 1. So I'm going to put that all in now. 1/5 x squared plus 1 to the 5/2 minus 1/3. This the 2's cancel, that 1/2 and this cancel. 1/3 x squared plus 1 to the 3/2. There you go. Okay, I'm going to stop now because the next section has a little bit of graphing, and so I just want to have that be its own video. And then the one after that is another type of thing for this section. So I will put those in separate videos. Okay, see you later.